All right, so during the last lecture period, I said that proton signals, when they show up on NMRs, are oftentimes more complicated than one singlet, meaning one sharp peak. They get split into these sub-peaks, right? And we said that depends on the number of 2 or 3 bond neighbors that you have, right? So for these examples, we were looking exclusively at proton HA. And we said if you have one 3-bond neighbor, it gets split into a doublet. If you've got 2 3-bond neighbors, it gets split into a triplet. If you've got 3, it gets split into a quartet. And if you've got more than that, you can use the n+1 rule, right? So 4 neighboring HBs would give HA a pentet. I wrote quintet. Most people would say pentet over a quintet. The important thing to remember is you can only be split by protons that are 2 or 3 bonds away. You can't be split by other HAs, meaning equivalent protons. And you can't go through any non-carbon atoms for the most part. So that was one of our big takeaways. We went through a few examples. We didn't cover the chemical shift aspect, meaning where they show up left or right on the spectrum, but we were just trying to anticipate integration, meaning the area underneath the peak, and then the splitting pattern for the peaks. I also just gave you guys a NMR study guide. Oh, there it is. And I do give you this, at least the front half, on exams. This shows you the approximate chemical shift, and we'll go over this in more detail today. But you can look at the type of proton, and you can say, oh, alkenes, meaning protons coming off of double bonds, show up typically around 4 to 6 ppm. The other important thing to remember with this is this key word, approximate, right? This isn't going to be absolute. This is just a rough guide that you can use to predict where they'll show up on your NMR spectrum. The other thing too is on the backside, it gives you a little bit more detail with the splitting patterns. So like I said, number of 3-bond neighbors, add 1 to that, and you can predict which peak you're most likely to get. You may notice too, down at the bottom, there's one labeled multiplet. That basically says that a peak looks really funny. You can't easily distinguish whether or not it's a singlet, triplet, whatever. It just looks like a hodgepodge of peaks. And so people will just call that a multiplet. And today we'll talk about why that's often observed. So let's go back and talk about signal splitting in a bit more detail. Let me change this a bit. 100%. There we go. And let's go back and look at an example. But before we do that, actually, let's define a coupling constant. So a coupling constant is the distance between the peaks. The distance between peaks in hertz when a peak is split. Okay, so let's take an example. And let's say I've got this proton, it's an aldehyde, and then this is just attached to some other carbon chain, and we've got 2 protons over here. So how many unique sets of protons do you think we have? And assume no chirality in this molecule. Should we have 1, 2, or 3? 2. Okay, so we'd say HA, and then over here we've got HBs, right? Assuming we've got no chirality in this portion. Okay, so HA, what should HA be split as? Will it be a singlet, doublet, triplet? Should be a triplet, right? It's got 2 3-bond neighbors, 2 + 1 means it's going to be a triplet. Let's try to mathematically understand why, though, and hopefully this will make sense. So let's say we've got an HA signal right here. Oh, let me change this to black. So this is HA, and it's unsplit. Meaning right now it's not feeling either of the neighboring HB protons. All right, what will happen is one of those neighboring protons will split it once, and then the other proton will actually split it again. So I'll show you guys kind of how this works. So what we're going to do is split this into 2 halves, right? So do you see on my graph paper, it's a little hard to see, but it's 4 units tall. We're going to split it into 2 even peaks, like this. And what this distance is called is your coupling constant. And coupling constants are normally shown as J values. So what they're saying is this is the magnitude of splitting by that neighboring proton. So we'll call this JAB. And that's basically saying HB splits it this wide. And then if we look at this, we'd say, all right, this is HA split by 1 HB, not by both of them yet. But we've got the second HB proton next door that can split this one more time. And the splitting will occur at an equal magnitude, meaning it's going to occur at the same width. So if we do this again, we would say, all right, if it's the same magnitude, that width should be exactly the same. You guys didn't think you need graph paper, huh? Yeah. And if we look at it, those two peaks are going to get split again. What do you think is going to happen in the center portion? It's going to form one peak, right? Because they're actually going to converge when they're split a second time. And so if we think about it being 4 total units, if we do this again, it's actually going to be roughly 2 units tall, right? And then what about on the outsides over here? How tall should that peak be? 1 unit. So if we look at it, we've got this and this. And this also goes back to explain the 1 to 2 to 1 ratio that we talked about in the previous lecture. It just happens that because the splitting occurs at that same order of magnitude, you get peak stacking, essentially. And if we look at this too, like I was saying, the splitting here is going to be the same, meaning the same width for the first split versus the second splitting pattern. Does that make sense? If we go ahead and we look at this peak, I'm going to zoom out a bit. I'm going to draw you a zoom in view. The first little peak on the side will probably look like that, and then it'll go over, and then you'll have a big peak right here. Oh, shoot. Try this again. And it'll look like that. So if you really, really zoom in on an NMR, you can actually see the peak splitting. The reality is they aren't perfectly straight lines. They tend to have what's called peak broadening. They look like little teepees. The better the NMR is, the sharper those peaks get. The worse the NMR, they get broad and kind of uneven, and that makes it hard to interpret sometimes. Does that make sense? It does get a little bit tricky. Let's take a look at another example. Let me go back and do this again. And these other examples, we'll go from easy ones to harder ones. Let's assume we've got this alkene. I've got a fluorine and a chlorine. And I've got a proton here. How many unique protons does this have? What's that? 2, right? This proton on the left is going to be very different than this proton on the right because they're in a completely different chemical environment. All right, so if we think about HA, what should that be split as?
A doublet.
A doublet, right? So HA should be split as a doublet. It is split by HB, right? Because that's the 3-bond neighbor. What about the one on the right?
A doublet.
A doublet, okay. And we'd say split by HA. And then when we think about these peaks, right? What we would say is, all right, HA we know is going to be a doublet. So I'm going to draw this. Oh. See if I can make this look nice. Like that. So this would be my HA doublet. And then over here, maybe I've got an HB doublet also in that same spectrum. I know this isn't the prettiest peak, but you get the idea. If you notice, the width of the splitting should be exactly the same, right? So what I mean by that is the distance between these peaks here versus here should be exactly the same. Because they're splitting one another, right? So the magnitude of splitting should be the same whether or not you're looking in one direction or the opposite direction. So what I mean by this is JAB is going to be equal to JBA, right? So it's kind of that mathematical operation. Oh, sorry.
Did that last video?
BA, there we go. Does that make sense? So J is your coupling constant in Hertz. And in this case, the splitting is the same. In both directions. Does that make sense? Now we've got to jump into the crazy, weird examples. And this is not my favorite thing to teach because it's conceptually a little bit challenging. Okay, so this one, we're going to only focus on one proton. And let's do a fluorine here, hydrogen, hydrogen. How many unique types of protons are there in this molecule? Three, right? If we look at this one, that's unique. It's on the same carbon with the fluorine. HB over here is trans to that fluorine, which means it has to be different than this one that is cis to that fluorine, right? So we've got three unique types of protons. And for this one, let's focus only on HA. We're going to ignore HB and HC splitting for right now and only look at HA. So if we think about HA, what would you think it should be split as? Let's think about it, right? How many 3-bond neighbors does it have? 2, right? So we should think it's got 2 3-bond neighbors. It should get split into a triplet. The problem is not all of the 3-bond neighbors are the same, meaning they'll actually split to a different magnitude, and that actually complicates things a fair amount. So let's take a look at this, and we'll do that same splitting thing I did before. So I'll say this is HA, this is unsplit. So nothing's split it at this point. And the tricky thing is the splitting for HC is actually going to be quite large compared to the splitting for HB. So let's do that one first. Actually, let me do this. Yeah, this is going to work. All right, so if we split this, just like before, we're going to cut it in half. So it started out as a peak that was 4. And so now what we'd call this is HA split by HC, right? And if we look at this, we could say this is the coupling constant for A and C, right? So the magnitude of splitting is quite large for A and C. A and B are actually a little bit different. So what we're going to do is split this, but this time it's going to not be as intense. The splitting is actually going to be smaller. All right, so if we look at this, we're actually going to get, whoops, peak, 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 and peak. We'll call this JAB. So does that make sense? The splitting for proton C that we labeled is very, very wide. But the splitting for B is actually a lot narrower. So rather than those 2 internal peaks overlapping perfectly and forming a triplet, they're actually slightly offset. And so what this looks like in an NMR spectrum, I'll zoom out and do the weird view again. So zoom in view. So you end up with something that looks like this. Adjacent, whoa, shoot. adjacent to something that looks like that. It looks kind of funny. What people do when they see something like this is they refer to this as a doublet of doublets. Confused yet? You can have doublets of triplets, doublets of quartets, triplets of quartets, quartets of triplets. It gets kind of goofy and weird really, really quickly. And the problem is quite often they're not as clean as this, meaning they don't separate out into unique defined sets. They just overlap like this, like two hands overlapping. What do you think they call that? A multiplet. They just say that's way too complicated. We'll just call that a multiplet. It's way too hard for us to analyze at this point. This typically only shows up in a meaningful way with alkenes. You can clearly see the splitting pattern with alkenes. Otherwise, people just call them multiplets, meaning if they're coming off an aliphatic system, the splitting is so close to the same magnitude, they overlap a lot, and you just get these confusing looking peaks called multiplets. Yep.
So what happened to the big peak and the JAC peaks?
Yeah, so the first splitting, like we saw, was HA split by HC. And down here, we've got HA further split by HB. So the first splitting was HC. That's the splitting that's the largest magnitude. And then that peak, once it's split already, you can theoretically split it again by HB. And so that one peak actually gets split into 4 even peaks that are offset from one another.
But why are those peaks not on the NMR?
What's that?
I said, is there any reason they don't show up on the NMR?
They do show up on the NMR. So the peak for HA on the NMR will show up as a doublet of doublets. It won't show up as a triplet, which is what most students would anticipate. And that, like I said, has to do with the fact that the neighboring protons aren't all the same type. And when you've got different types of neighboring protons, you oftentimes get this funky splitting pattern. Yep.
What determines whether HB or HC splits it first?
That's a good question. It honestly doesn't matter which order you do it in. The end result will be the same. Traditionally, though, people will start with the largest magnitude one first and then go to the smallest ones later just because it's easier to map out. Then the trickier question is, how can we anticipate which ones will be the larger magnitude splitting versus the others? And that's something you won't learn unless you go to chemistry grad school for the most part. It can be really tricky. For the most part, trans is always going to be bigger than cis, and that's the easiest one to remember. But beyond that, it gets pretty crazy. Yeah.
So this human view would be labeled as with the H or JAB.
What I would do is, if you zoom in on this and you see 2 doublets right next to one another, really, really close to one another, there's a chance that they could be a doublet of doublets, meaning one peak split into a doublet of doublets.
But
Yeah.
Would it be labeled as the JAB, or would it? Like, how would we label that peak? The last one we labeled.
Yeah, so the first order magnitude splitting is the JAC followed by JAB, and then on an NMR, most people would just say DD for doublet of doublets, and they would have an arrow pointing to that peak. Yeah. So don't write D because people will think that's a doublet. DD means doublet of doublets. Good questions. Sorry, I know that stuff's complicated, but it confuses students, and I feel like I've got to show it to you because you may run into it occasionally. All right, now we get to go into the easier stuff. Interpreting or anticipating chemical shift, that's referring to how far left or right peaks show up on the NMR spectrum. Like I said, I give you guys that cheat sheet this term, but I don't give it to you third term, so after you deal with this over and over again, you start to see a pattern. So let's dive into this chemical shift aspect, and there's actually a formula for it. And the symbol for it, is that, I'm trying to remember. Delta, yes. I wanted to say tau, but I knew that wasn't right. It's going to be the observed shift meaning the distance from TMS in hertz, times 10 to the 6 Does anybody know what TMS is? Not quite. You guys remember it from protecting groups? What was it in a protecting group? Yeah, protected OHs. It was a silane, right? When we were protecting alcohols, it was trimethylsilane. In this case, it's tetramethylsilane. So T will work in either case. So we'd say TMS is tetramethylsilane. That's kind of the reference standard used in all NMRs today. And then the other half of this equation is the operating frequency of your NMR. In hertz, right? NMRs vary a lot. So for example, the NMR that we use is 60 megahertz, so that would go on the denominator side. There are NMRs that go all the way up to 1.2 gigahertz. Those are the fancy ones that are used to study protein folding for the most part. So there's a huge range in NMR powers. The lower operating frequency NMRs are permanent magnets, meaning the magnet just sits there and does its job. The really, really fancy high operating frequency NMRs have electromagnets in them that are cooled with liquid helium and liquid nitrogen so that they're superconducting magnets. So that does change the chemical shift, and you do have to account for that. All right, so I'll show you guys a little bit of this scale again. So let's say we've got an example down here. The range, if you remember, goes from about 0 to 15, and the units are in parts per million. Down here, the reference signal, the TMS peak, is always set to always set to 0 ppm, and your actual range of peaks will fall typically in this area unless you're working with some sort of exotic system. There's a variety of different things that will cause it to show up either more towards that 15 ppm side or closer to the 0 side on your NMR, and I'll get into that in a second here. So let's see the two main things that affect it. So two main features affect shifting. One is electronegativity. Or induction. And I'll show you guys kind of the simplistic view of this. This isn't the absolute right answer, but it's a simple trick you can use. This really only works to a point. And so what I tell students is 5 ppm and below, you can actually use this as a rough guide. And what I mean by that is the closer you get to 5 ppm means it's more polar, meaning the proton's highly polarized, it's close to an electronegative atom, right? So those show up closer to 5 ppm. So maybe it's a proton adjacent to a carbonyl group, right? Those are highly polarized. They can show up really close to 5 ppm. If they're not near anything that's polar at all, they tend to be really close to 1 or 0. And that's a nice simple trick you can use when you're looking at that region. All right, the second one gets a little bit funky. This is due to aromaticity. And the fancy name for this is the anisotropic effect. And again, the really kind of dumbed down simplistic view of this is, again, we've got this range from about 0 to 15 ppm, and I'll fill it in. Basically says that aromatic protons tend to show up in this range from about 6 to 9 ppm. And this has to do with this weird phenomenon of aromatic molecules. And what I'm going to do is draw an example aromatic molecule on its side. So this is going to be benzene, kind of with a side-on view. Does that make sense? And if we think about benzene, right, it's all sp2 hybridized. So we've got these p orbitals sticking straight up and down all the way around this ring system. And the electrons in the aromatic ring system kind of float around in a circle, right? They're delocalized across the entire ring. Those of you that are taking, I think, second term physics are probably covering this right now, but when you've got charged particles rotating around, what do? What do you create? Magnetic field, absolutely. So when these electrons move around, you actually get this magnetic field kind of going up and out of your ring. This is my artistic representation of that. But if you're a proton, right, and you're coming off that aromatic ring, all of a sudden you're in this unique magnetic field due to the aromatic delocalization of electrons. And so that's what causes them to shift into a really unusual position. If you normally think about a CH bond on an aromatic ring, you'd say that's not polar, right? That's a really non-polar bond. Why is it showing so far to the left on your NMR spectrum? And that has to do to the induced magnetic field. Other than that, like I said, I'll give you guys that cheat sheet, and that can be incredibly helpful. All right, last but not least, we've got the easy one. Carbon NMR. So carbon NMR, in my opinion, is way easier than proton NMR. There's a couple things that are important to remember about carbon NMR. It is way less sensitive. In fact, so much so that our NMR that we have, because it's 60 megahertz, we'd have to run samples overnight to get a decent carbon NMR spectrum. So we're not going to do that in lab. All right, and why do you think it's less sensitive?
Only 1.1% above.
Yep. Carbon-13 is only 1.1% abundant. Why can't we look at carbon-12? It's an even number, right? We can only look at nuclei that have either an odd number of protons or an odd number of protons and neutrons, right? So in this case, carbon-13 is really our only chance to look at carbon. The other nice thing is that there's usually no splitting, meaning you don't have to worry about doublets, triplets, quartets, etc., unless you're doing a fancy experiment, which our textbook doesn't even cover. The other one is usually no integration, meaning the area under the peak means nothing. You can't use it to correlate out to number of carbons like we could with the proton NMR, so we don't have to worry about that. Really, the best thing that it tells you is the number of unique carbons. Number of unique carbon sets. So just like your pod that you did a few days ago, you anticipated the number of unique carbon sets, you can correlate that to your carbon NMR. The other thing too is that the chemical shift corresponds to functional group. Meaning the carbon that's attached to a CO double bond is going to show up at a very, very different chemical shift or ppm than something that's attached to a methyl group, for example. So you can use that really quickly. The other goofy thing with carbon NMRs is the range is entirely different. So the range for a carbon NMR goes all the way out to about 220 ppm. So the range is huge. So that's something to pay attention to, is you're no longer looking in that 0 to 15 ppm window. Instead, you're looking at 0 to 220. The other thing, too, I did want to show you guys is when you take a sample compound and you want to take an NMR of it, you don't typically put it in as a 100% pure compound. That just doesn't ever work. What you normally do is you actually run it in a special solvent. Does anybody know what type of solvent you have to use? You normally use a solvent without protons on it, right? Because you don't want it showing up in your proton NMR. So what they do is they swap out all of the protons for deuterium atoms, right? Deuterium, H2, is silent by NMR. And so typically in carbon NMR, students will come up to me and they'll say, what are these peaks around 77 ppm? It normally looks like a triplet like that. This is your solvent peak at 77 ppm. So you can ignore that triplet that shows up. Normally it's pretty small. Just ignore it. That's from chloroform. That's typically our solvent of choice when we're doing carbon-13 NMR. So something to be aware of. All right, there's a bit more too. So let's go back to that study guide. And so you can see up here, there's approximate chemical shifts, and there's a few things I wanted to go over. If you look at this one, this basically tells you protons coming off carboxylic acids are normally about 10 to 12 ppm, so that's pretty easy to spot. The other thing that's kind of cool is it's similar to IR. What happens to those peaks in IR? Are they sharp? No, they broaden out. That also can be observed in NMR. Sometimes that actually becomes a problem where they broaden out so much that you can barely see them. But I won't try to trick you guys. I'll let you guys know if there's a peak that's broadened out so much that it's hard to see. Aldehydes also show up really far downfield, meaning closer to that 12 or 15 ppm. Like I said, aromatic peaks show up 6 to 9. Alkenes show up about 4 to 6. Alcohols, just a generic alcohol, can show up at a huge range. So a generic alcohol can show up anywhere from about 1 to 6 ppm. It's not very reliable, and that's due to the fact that it H-bonds differently depending on concentrations, right? The other thing to pay attention to is this right here. People get really confused when they see X in this circumstance. So X in this case just means some sort of electron withdrawing group. So let me make a note of that. Meaning something's pulling electron density away. Usually it's a halogen, but really anything that's electron withdrawing can fall into that X category. The other one too is, what does AR mean here? Aromatic, right? So a methyl group coming off of an aromatic ring probably shows up about 2 to 3 ppm. And then you can kind of use the other ones as generic guides too, right? So protons coming off primary, secondary, tertiary carbons fall in the 0 to 2 ppm range. You can again use this same sort of logic with the carbon NMR, and you can see the range in this case is way wider than what we saw in proton NMR. And typically the carbonyls, meaning all of them, will show up really far downfield. So whether that's an amide, ester, carboxylic acid, ketone, or aldehyde, typically shows up around 200 ppm. The triple bonds and double bonds show up kind of in the middle, and then all the single bonds show up down here. Normally I try to get as much data as I can from the proton NMR and then use the carbon NMR as backup, or use it to fill in some sort of gap if I'm struggling, if that makes sense. The other thing that Klein does that's really, really useful is he gives you this guide at the end of the chapter to narrow it down even further. So this is a mathematical tool you can use to predict chemical shift for some of these unique circumstances. So for example, over here it says protons coming off of a methyl group typically show up at about 0.9 ppm. Protons coming off of a secondary carbon typically show up at about 1.2 ppm, and then tertiary carbon protons show up at about 1.7 ppm. Those are our benchmark values, or at least that's what he calls them. And then what you can do is add or subtract numbers to these values depending on neighboring groups. So for example, in this one over here, it's saying we've got a secondary carbon, which is this guy. So the benchmark value is 1.2. And then because it's next to an oxygen, we're going to add 2.5 ppm to it. And that means it's going to show up more downfield, closer to 3.7 ppm. This is surprisingly accurate. So you are allowed to use this on exams. I projected this up on the board, and you can use this to help problem solve a bit more. So this works for oxygens, for alcohols, or ethers. You want to add 2.5 to that benchmark value. If you're attached to the oxygen of an ester, then you want to actually up that to about 3.0. And so in that case, a secondary carbon with protons on it would show up closer to 4.2 ppm. If you're a secondary carbon and you're just attached to a carbonyl group, so maybe a ketone or an aldehyde is next door, then you only add 1.0. And so you can figure out the ppm there. And when this is really helpful is I'll show you an example. let's say I've got these protons. I've got these blue protons over here, and I want to compare them to the green protons on the left-hand side. What will the splitting be for the blue protons? So for these blue protons, how many 3-bond neighbors do they have? 3, right? Because we've got these methyl group protons right here. So the blue proton should be split into what? A quartet. Specifically, it'd be a 2-proton quartet, so the integration value should be approximately 2. All right, let's do the same thing with the green ones. What should the green protons show up as? Quartet. And again, they'll integrate as 2. We've got ourselves a problem, right? They have the exact same splitting, they've got the exact same integration, but this trick that we've learned can actually be useful for determining which one will land where, right? So the blue one, where do you think the blue one should show up? 4.2. Whoops, let me keep the color the same. So this will show up at 4.2 ppm versus the one on the bottom, where will that show up? Yeah, at about 2.2 ppm. So this can be really helpful when you're trying to peak pick and assign protons to specific peaks in your NMR spectra. Does that make sense? Don't brute force memorize this. I'll give this to you on exams. I just want you guys to practice your problem solving skills. So what I've given you guys is not a pod. I'll give you guys a break. I gave you an in-class activity that's a bunch of NMR problems. And part of the reason I do this is if you've had a chance to look at the labs for this week, it's a bunch of NMR work, which means there's going to be a lot of waiting. So what you can do during the lab period is actually work through these problem sets. I'll give you a second one tomorrow, but try to answer as many of them as possible and assign peaks to them too. And try to work with partners or in small groups as much as possible. So we do have a couple more minutes. You're welcome to get started on the first couple in class right now and see if you can get it. The other big hint I'll give you too is HDI is also useful for NMR. It's not just useful for mass spec and IR. So if you can, try to use the HDI formula that I taught you before. That tells you the number of rings and pi bonds.